All right, so let's go ahead and get started with the basic definition and responses of filters. And I know that several of you probably have seen this type of things in undergraduate courses, but if not, it would be a good introduction and a good reminder for those of you who have seen those. So we're going to basically synthesize the filters based on the scattering parameters that we have learned in the first course of that series. And that's not to say that that's the only way to synthesize a filter, but that is by far the most common way, and that's the way that basically gives you most of the tools, including the coupling matrix tool that we will be using here. So anytime you see a scattering parameter in this design, it's basically the ones we have discussed before. Typically, we start by defining two main parameters of the filter. One is the power transmission response, or as we've called it S21, and the other is the input reflection response, or as we call it S11. Now, as you may well remember, if your filter is totally lossless, specifying the magnitude of one basically gives you the magnitude of the other. So clearly we have learned that S21 square plus S11 square for a lossless network is only equal to 1, and so typically it's sufficient to describe one of them. In lossy scenarios, the situation changes quite a bit. So for example, if you look into a bandpass case, like the one that you can see here, there are going to be some reflection zeros, which you can basically see here. These are essentially the frequencies where your S11 is identical, equal to 0, in which case then your S21 should be identical, equal to 1. And then there are going to be other frequencies. Your S11 is simply below a threshold. In this case, it's 20 dB, and that means that your S21 must be above a threshold, must satisfy an insertion loss requirement. Also, it's true that most filters are going to be reciprocal, at least the ones we'll be discussing here. So it really doesn't matter if you specify S12 or S21, but specifying S12 is truly awkward. No one talks about S12, everybody practically talks about S21. Lastly, I want to remind you that reciprocity does not mean symmetry. So do not make the mistake that assuming that for filters the S11 will be equal to S22. A lot of filters are not symmetric, so they're not going to be basically the same. Now, an area where we're not going to spend too much time for the remaining of the class, and so I want to spend a little bit of time talking about, is group delay. So typically, when you specify a filter in advanced, at least, applications, you specify both the magnitude response as well as the group delay response. Essentially, group delay means how is the phase of the signal impacted when the signal goes through the filter. As I mentioned before, in this class, we're going to ignore group delay. We're only going to synthesize things based on magnitude. But I do want to show you the impact of that, and at least so you can understand what we are essentially leaving out. So a typical group delay is basically shown here as a function of frequency. And as you will normally see, a group delay, it's relatively flat, as it should be. An ideal group delay is basically independent of frequency. That means all frequencies propagate with the same speed through the filter. But unfortunately, close to the transition bands, this could be the transition band basically of a bandpass filter, you will basically get those type of peaks. And it's those basically type of peaks that cause trouble. Now, unfortunately, the more selective the filter is, the worse those peaks become. And so usually there is a trade-off between how much you can deviate from flatness and how much selectivity you basically want to have. So it's usually those peaks in the transition bands that will dominate the group delay issue.